Welcome to Chemistry 1, Chapter 3, Method Evaluation. In this section, you're going to find more review of your Intro to Clinical Laboratory Science course, which is always good. We're going to review the statistics, standard deviation, coefficient of variation, and then we're going to talk about the Westergaard rules, and we're going to move on to some new things too. So make sure that you continue on, even if some of this looks familiar, that you watch the whole thing. All right, statistics is the science of gathering, analyzing, interpreting, and presenting data. Three common statistical tests are the mean, which is the average, the median, which is the middle, and the mode, which occurs most often. First, we're going to look at standard deviation. I am not going to go over all of the calculation for standard deviation. I will add that in my lab math video within the course if you want review, but we're just going to go over what it means. Standard deviation is the dispersion or the spread of data around the mean. The wider the variety of points, the larger the standard deviation. For example, if your low number is 90 and your high number is 105, that may have a low standard deviation. If your low number is 5 and it goes all the way up to 250 and you have that huge spread for 5 to 250, that's going to have a larger standard deviation. So, it's important to know, looking at your Gaussian distribution here on the right, that 68% of the population falls between -1 and +1 standard deviation. 95% falls between -2 and +2, and a whopping 99% of people fall between -3 and +3, which is pretty much why we don't see the need to go beyond 3 standard deviations when we're talking about statistics. Very few samples would be included. The coefficient of variation sometimes is used to compare data. For example, if we're looking at two different chemistry analyzers and we're trying to decide which one is the most accurate and has the best precision, mostly precision, we would look at the coefficient of variation. What we would do is take the standard deviation divided by the mean times 100, and an indicator of good precision would be less than 10%. Here's some new terms that we're going to bring up in clinical chemistry, and we're going to do some calculations with these. Sensitivity and specificity. Sensitivity refers to patients with the disease that truly positively have that disease. For example, if you go to the doctor and you think you're pregnant and they tell you you're pregnant, you want them to have great sensitivity with that. You want them to know that, okay, you just got pregnant and we can tell you you're pregnant. That's good sensitivity. Specificity is the number of patients without the disease who test negatively for the disease. So you're not pregnant, they tell you you're not pregnant. You don't want to go in and not be pregnant and have them tell you that you're pregnant. Okay? So if you're not pregnant, you want them to tell you that you're not. Now we have some other issues that come into play that you need to know in order to be able to figure out sensitivity and specificity. For example, a true positive. A true positive is a patient with the disease that correctly tested as having the disease. This is a patient that goes in for a pregnancy test, and it comes out they are pregnant, and they really are pregnant. That's a true positive. That's what we want a lot of. Okay? Then we have true negatives. Those are the patients without the disease that are correctly tested as not having it. So you go to the doctor, you get your pregnancy test, it's negative, you really are negative. Now we have some other issues that come up that are not so desirable. False negatives. These are patients with the disease and the test comes up negative. So you're pregnant, you go to the doctor, they tell you you're not. That is a false negative. A false positive is the patient without the disease that are tested as having it. So this is where you're not pregnant, you go to the doctor and they tell you you are. Oops. So false negatives and false positives are not the best situation. So these are two calculations you're going to have to be able to use. Sensitivity, which is kind of figuring out how low can you go. So for example, I go to the doctor and let's say I'm 1 week pregnant. If that test is able to pick up the fact that I'm pregnant that early on, it can pick up such tiny amounts that is considered very sensitive. We can calculate the sensitivity of a test by collecting all the data from a bunch of people, which is what they would do for a new pregnancy test going out on the market. The number of true positives, okay, so let's say you have 10 true positive patients, divided by true positive plus false negatives. So let's say then you have 10 true positives plus you had 3 false negatives. That would be your sensitivity. The closer you are to 100%, the better. Specificity takes the true negatives divided by true negatives plus false positives. Okay, so that would be more specific. For example, you go to the doctor, you think you're pregnant, and you don't want another test to interfere. So let's say something else interfered and said you were pregnant, but you're really not. Okay, so true negative divided by true negative plus false positive will give you the specificity of that test. Sensitivity is how much of it, if you're very, very, very barely pregnant, how much it can pick up. Specificity is the fact that you're pregnant, you really are, not that you have another disease and it's showing up that looking like you're pregnant. When we look at selecting different types of analyzers and methods that we're going to use in the laboratory, we have to look at a lot of different things. Please don't memorize this list. I'll let you know in the next couple slides what's important. You need to consider the cost of it. How many tests can you run on it? The personnel requirements, does it take one person or 10 people to run it? What is the cost per test? What type of specimen do you need? How big is it? Does it fit in the corner of the room? What are your power and environmental requirements? Do you need to plumb it into the plumbing system, or does it have its own containers? What about the sensitivity and specificity? Okay, you want to make sure that it picks up tests that are at a low enough level and that it diagnoses people correctly. What's the detection limit? The linear range, that's important. You can write that down here. Linear range is how low and how high can you go. Interfering substances, is there a lot or is there a few? And the estimates of imprecision and inaccuracy. What level of that are we going to look at with this type of method that we might be looking at? The first thing we're going to do is a precision study. This estimates random error associated with the test method. This is done over 20 days, so you're going to run it, controls and specimens 1 to 2 times a day. Meanwhile, you're using your old analyzer, if you have one, at the same time. Next, you're going to do an accuracy study, and you're going to compare the methods. So you're going to see if you're looking at 2 new analyzers or if you want to look at your old one compared to a new one. You're then going to validate and establish a reference range, and usually the manufacturers of these analyzers do help you with that. You want to compare methods. When switching from one method to another, you run patient specimens on both the old and new method. So if you have analyzer, old analyzer and you've got new analyzer, you're going to run the same specimens on both. You're going to put the old method on an x-axis and the new method on a y-axis, and you're going to compare the data. We want to see a linear regression analysis. Don't worry about having to know the definition of that. We're going to look at the standard deviation, which shows the dispersion, like how far apart, how different are they. 2 types of error are measured with those methods as well, random or systematic error. Random is present in all measurements. It's usually due to instrument, operator, reagent, or environment type of variations, and the standard deviation can help in estimating that. Systematic should not be present in a method at all. 2 types of systematic error that you don't want to see is constant. This exists when there's a constant difference between the test method, a new one and an old one. And then there's a proportional difference. The difference in the test of the old are the same. So it's either really, really high in one analyzer and really, really low. You know what I mean? They're proportionally different. Then we're going to look at reference ranges. The reference range, a normal range, is the usual value for a healthy population. The test result is compared to the normal range. Due to diversity of populations, labs need to determine their own reference ranges. For example, if you go to Green Bay, Wisconsin, and you get a test done, and then you go to Denver, Colorado, and get a test done, the reference ranges are going to be different. Mainly because we are closer to sea level, and the people in Denver are really up high. So there's going to be a variation in what the atmosphere is doing to their blood levels, actually. Usually, they want a minimum of 120 samples in each age and sex category to determine a reference range. Smaller hospitals may analyze a minimum of 20 to verify a reference range. It just depends. Then we run quality control. Quality control is always done to monitor analytic processes. We run liquid samples through the machines or analyzers to make sure there aren't any errors during analysis. This is usually done once a shift or once a day, depending on what the manufacturer recommends. We run it just like a patient sample, and the controls closely resemble patient samples. More than one level of control should be run. and it must be acceptable before you can release the patient results to the physician. So we always want to make sure our quality control looks good before we result those patients. We have a couple types of controls. First one's called an assayed control. This one is where the manufacturer has set up control ranges for each test, and it comes with a list of values. That's what we use in our Rasmussen laboratories. And then there's unassayed controls, which is where we'll need to establish our own on those controls. The more common, I would say, is assayed. We want to look for random versus systematic error. Random error affects precision, so it increases maybe due to variations in technique, or there could be air bubbles in your lines, or there's a number of things that could happen. Systematic errors are due to factors that have a constant difference. For example, if the standards are poor, the reagents are poor, failing instrumentation or poorly written procedures can cause all of a sudden your QC to just not work. We had a situation one time where our reagents were sitting out at a shipping dock in the middle of winter and they froze. When we received them, we took them out of the box. We thought they were fine, put them in the refrigerator. The tech took one out of the refrigerator, put it on the analyzer, and it wasn't working. Come to find out, they froze. Well, she took it off the analyzer, and when she looked at it more carefully and shook it, there was a big chunk of ice in the middle of it. So that would be a systematic error. She couldn't get her QC to work to save her life. It was frozen. Some of the quality control rules, I'm just going to read through these quickly because you were exposed to these in the intro course. There are more here than what you may have had exposure to, but that's okay. Westergaard rules are used to interpret our QC. If you have a 1-2S, that is a warning where one control level exceeds 2 standard deviations. So that's a warning. 1-3S is an rejection. It's usually some type of a random or systematic error where it exceeds 3 standard deviations. 2-2S, which is usually you had the 1-2S one time, now you're going to have it happen again, and that would be a rejection. 2 points out 2 standard deviations. R4S is one observation exceeding the mean plus 2 standard deviations and another exceeding the mean minus 2 standard deviations. So you can have, this could be across 2 levels of QC. 4 consecutive observations exceeding the mean would be a 4-1S. So if you have 4 points between 1 and 2 standard deviations on one side of the mean, that could be a rejection. 10x, that's all 10 on one side of the mean. So I guess the only one that's really new there is the R4S that you probably haven't really looked at. Alright, look at all levels of the control ran. It's the first thing you want to do. Check and see if any are out 2 standard deviations. If no, keep going. If yes, look at the Westergaard rules and see what has been violated. The beauty of this is we have the analyzers and computer systems that do a lot of this for us. Very few labs have no type of computerization to do this. I worked at a lab in college where we had to put the little dots on the Levy-Jennings chart for hematology, but that's going to be very few and far between nowadays. The questions to ask: is there only one level of control out 2 standard deviations? Is the control out 2 or 3 standard deviations? Have the controls been falling on one side of the mean? And if only one level of control is out 2 standard deviations, was the prior control run acceptable? If it was, take it as a warning and run your patients. We look at these Levy-Jennings charts to compare values over time. I have a Levy-Jennings chart down here on the bottom, and this shows a nice distribution across the mean. You want it to go back and forth and up and down. If it's all on one side, that's not good. Okay, you want it to be scattered about like this. Our control ranges are calculated from that mean and standard deviation. So in this case, it looks like the bottom would be 199 up to 202. That's minus 2 to plus 2 standard deviations, which would be our control range for this one. A shift would show a sudden change. All of a sudden you're going along happy and then boom, everything comes up high. A trend is when it just starts slowly going down or slowly increasing. Things that could cause a trend that I've noticed is as your QC or your reagents get old, towards their expiration date, they'll start creeping out on you. Another term you need to be familiar with is a delta check. This is the most recent result of the patient and is compared to the previous one. Here's an example. A patient has a glucose level drawn at 6 a.m. and it's 89. They have a glucose level done at 10 a.m. It's 410. That's a delta check. The analyzers and computer systems are set to flag you when there's a change in results so drastic that it's not typical. Now, something that could happen, like with what I just mentioned, where you have a glucose 89, then all of a sudden it's 400, could be maybe they drew above a IV line that had a sugar substance in it, that maybe some type of a nutritional TPN or something would cause something like that to happen. So we'd call the floor and ask if that would be the case. So that's just an example of what a delta check could be. You just want to make sure that it's not an analyzer error and that there really is something seriously wrong with the patient that would cause that to happen. With quality control, we also do some external quality control. We learned about this in intro as well. Proficiency testing. We provide samples of unknown amounts to labs to be tested as normal patient samples. So you might get some from the state lab, or you might get it from CAP. And they come in a box with a sheet of paper. It'll say, run these tests on these samples. So you do. You write down your results and you mail it back. And you hope that yours compare to your peers closely enough that you don't get in trouble. Obviously, you want it to be in the area of what the proficiency testing facility wants you to have. Point of care testing also needs quality control. Point of care testing refers to testing performed outside of the lab and can be by lab personnel versus non-lab personnel. Medical assistants and nursing are a few. And there's a fast turnaround time. It requires ongoing evaluation of the equipment, education and training, and quality control. Examples are those little glucose analyzers that the nurses and medical assisting people use on the bedside, or in the, let's call it bedside or patient side, that they can get the results immediately. Just because they're a little tiny analyzer doesn't mean that they don't have to be monitored. There is a lot of control that goes on with those, usually by somebody within the laboratory. You will have to do a paper this quarter on point of care testing, and the information on that paper can be found in Module 1. When we look at the testing process, we covered a little bit of this early on, but the preanalytical testing process, we have to make sure the patient is ID'd properly, the patient is prepared properly if they're supposed to be fasting or anything. Do we collect the specimen properly? Do we transport it to the lab at the correct temperature? Was it processed correctly? Analytical is where the documentation of the analytical protocols are followed. We monitor technical competency of those people running the test, and any statistical control and analytical methods need to be followed. Post-analytical, of course, is the reporting of results. All right, that concludes our 3 chapters for the first week of Chemistry 1. I know it is a lot. Just review and the PowerPoints as best you can. Use the book as a reference tool more so than a large reading material, and you'll be fine for the quiz in Module 2.